Okay, so I didn't get to as far as I wanted to in my previous video, so this is going to be the part 2 of video 3 for magnetism basics. We last off finished with transformers. Let's move on to capacitors. So a capacitor is an energy storage device. It stores energy in the form of an electromagnetic field, and the measurement used for capacitors is the farad. There's two different styles of capacitors you'll see on wiring diagrams. You got one symbol here and another symbol here. The difference between the two capacitors is the capacitor over here is polarized, which means it matters the way you hook it up. This one, you can hook it up either way, this side to the positive, this side to the negative, this side to the positive, this side to the negative. It doesn't matter which way you hook it up. This one, it does matter. If you hook it up wrong, most likely you will blow that capacitor. Now let's get into actually what is a capacitor and how it works. I drew a little diagram over here. This is your capacitor symbol here. And I have my 12-volt battery and I have a load here. What's going to happen is we're going to have current that flows through the load. It's going to form a whole function. It's going to go around. It's connected to a negative. Let's say that's a light bulb. Let's say this here is a light bulb. That light bulb is going to be on. If we were to, without the capacitor here, if we were to take this and cut that open, that light bulb would instantly turn off. Let's say that's a switch. Let's say we have a switch right here. So if that switch is open, that light bulb's not going to shine. If that switch is closed, that light bulb's going to shine. The way a capacitor works is you got two metal plates. These are the two metal plates. And in between, there's a dielectric material. What a dielectric insulating material is, it's an insulating material that can be polarized when it's applied by an electric field. So what's going to happen is we're going to have current that flows. It's going to flow this way. It's going to turn that light bulb on. It's going to keep flowing. When it's flowing, we're going to have a buildup of positive charge on this side. It's going to maintain a positive charge all over on this side. And on this side, we're going to have a buildup of a negative charge. And what's going to happen is, as soon as we open this switch, get rid of this, we're going to have current that flows from the capacitor. The capacitor is going to end up acting like a battery with a stored electrical charge. You can have that capacitor store huge amounts of energy. Depends on what kind of style capacitor you have. But let's say this is just a normal, regular, smaller capacitor. Now that we disconnected this, this is disconnected. Current's going to flow around here, and this light bulb is going to maintain on for a short while it drains this capacitor. So when you have things like airbag systems, you have capacitors built into your airbag sensors because they have to store the energy. You have to store any sort of cut voltage from an accident. Otherwise, let's say your battery doesn't work and you get into an accident, then your airbags wouldn't go off if you did not have capacitors. Another function of capacitors is when you have things like alternators. When you have alternators, I'll get into this in a different video. I'll make it very brief. But alternators create AC current, sine waves like this. And they have it in three phase. So you're going to have multiple AC waves put all together. It's going to form a function something like this. Sorry for my bad wave drawing. But then they're going to have diodes, which act as electrical one-way check valves. I'll explain those in a later video. And they'll cut this current in half. So it'll only use the DC part, not the AC part. And then what's going to happen is you're going to have a capacitor built into this system that's going to absorb the power, and on the low power pulses, it's going to smoothen it out. So what's going to happen is when you look at that reading, it's going to look something like this. It looks like a very consistent DC voltage. it's not going to have these drops in between because the capacitor is absorbing that energy and releasing it on those lower pulses. And again, measured in farads or microfarads. Let's talk about relays. You got quite a few different relays. You can see on this drawing here, we got an inductor here. When we're controlling relays, we're controlling an inductor, which is acting as a magnet, and that magnet is going to close a switch, which is going to allow current flowing into a whole nother circuit beside it. So the way a relay works, you have a small amperage. So we have 12 volts at like 0.2 amps. And that's controlling this circuit that once it's closed is going to be 12 volts at like 20 amps per se. That's how relays work. You have a very small signal wire controlling a higher voltage system. Now, relays have pinouts, so they have diagrams. Your standard 5-pin mini relay, this is the setup they have. They have 86 as your input, and keep in mind, it is necessary to have 86 as your input. 86 is your input for your inductor coil, and 85 is your output for your inductor coil. So this is your control system. I have them written down here, control circuit, positive and negative. And then I also have this is just another diagram. They might not use 86, 85, they might use 1 or 2. Relays, they don't always go with the same numbers. Then we have 30 as our input for our high current switch circuit. That 30 is going to supply on a 5-pin relay 87A and 87. Your 87A is going to be your normally closed. That's where your switch is going to want to sit, is on 87A. So current always flows through this relay when this coil is not energized. When it does get energized, it will flow to this circuit. On a 4-pin mini relay, what you're going to have is the same system as a 5-pin mini relay, but you will not have a normally closed circuit. You see up here we have this 87A. We don't have that over here. We have nothing. So we have no current that flows through this relay unless this coil gets energized. With our switch circuit, we have a supply of 30. Our normally closed is 87A, and our normally open is 87. If we're using this other diagram numbers, it will be 3, 4, and 5. We have an ISO micro relay. This is using the basic 1 to 5 number types. And on a 5-pin, it works exactly the same way as the other relay. You just have a different pin layout, but it works exactly the same way. You do have that field coil, and it is switching between them. So you see 4, that's our normally closed system. 5 would be our normally open system. 3 is our switch supply, and 1 and 2 is our inductor circuit, our control circuit. This one, same setup, just does not have your normally closed system. One thing I want to say about relays, the reason why 86 and 85 matter is because when we talked about inductors and the collapsing of magnetic fields, now they're going to have things like diodes in there. And the way a diode works, it's a one-way check valve, a one-way electrical check valve. And if you have a diode and it lets current flow this way, but it doesn't let current flow back, and you put them opposite, you're putting that diode, so it's going to act as a straight wire. It's going to be a straight wire that goes across. That's going to short. That's why it is important to have 86 as your input and 85 as your output. Now, I will say there are some, they'll have a resistor instead. And if it has a resistor, then it doesn't really matter which way you put it. But regardless, just be cautious that 86 is supposed to be the input. Let's talk about solenoids. There's a few different types of solenoids. Let's talk about discrete solenoids first. Discrete solenoids have only two positions. They have a fully retracted and a fully extended position. Basically, what you have here is you have that magnetic iron core in the center, as we talked about before with inductors, how they turn into electric magnets when we put ferrule material in the center. We have a spring, this spring in the top here, that sets our one position. That is a fully retracted position once that spring is fully pushing that down. We have this field coil that controls and turns it into a magnet. And what it does is when we put current to it, it's going to want to push that piece of metal up the same way a magnet works. Magnet wants to pull. With this electromagnetic field, it's going to pull that ferrule material up and it's going to connect to something. So you're going to have some sort of linkage here, some sort of system. You have some sort of linkage there. And you're going to have something that gets actuated by an electronic solenoid. Whether it's opening and closing, let's say this is a hydraulic pipe. You can have this open and close this just by actuating an electronic signal to that field coil. Latching solenoids, they have two positions as well, but they don't have a spring per se. When you energize this coil one way, it will move the inside piece to one side, which is going to move it to one direction. And then if you energize it the opposite way, it's going to move it to the opposite direction. And these magnets on each side are going to hold it in position. This is what's used on things like door locks, for instance. Proportional solenoids. I know we did not talk about pulse width modulation yet. Basically, what a pulse width modulation is, I'll get more into it into a later video. It is, instead of supplying a constant voltage, it supplies a pulsed voltage, and that pulsed voltage, that solenoid will read the average voltage of that pulse. So the bigger gap you have in between pulses, it's going to act like a smaller voltage. So this would be, let's say this is 3 volts, and let's say this here would be 6 volts. Just because of the gapping in between of the pulses of electricity. I'll get more into that into a different video. I just want to bring out proportional solenoids. You are basically pulsing this field coil to control exactly how much voltage it's getting in that field coil and how strong that magnetic field is going to be. So you can have things like, for example, this is used on hydraulic brakes, or you have hydraulic fluid that wants to flow this way, and you want it to flow this way, or you want to close it off, like on an ABS system, for instance. And you'll have proportional solenoids either close off the supply and pulsate the fluid out to let it return back using pulse width modulation proportional solenoids. And so you basically have a variable position. You can have it half energized, half open, and you can have it fully open. You can have it 3/4 open. You can have it a quarter open. You can totally control it just by how much voltage you're sending to it. I think that'll basically summarize what I wanted to talk about for my video 3 magnetism. Uh, Stick around for my next video. I'm probably going to get into diodes and wiring, how is wiring measured. Thank you guys for watching.